When China's rocket lifted off, launch cameras caught something strange. White debris was falling away from the vehicle, and it immediately raised alarms. At first glance, many assumed it was harmless, just like the ice that sheds from American rockets, such as the Saturn V. But this time, that explanation doesn't fully hold up, because what was falling from China's rocket wasn't just ice. And in the past, similar debris has led to catastrophic failures. So, what exactly was that white material? Was it normal? And more importantly, does it represent a real launch risk for China's space program? To answer that, we first need to understand what typically falls off US rockets and why it usually isn't a problem. In most American launches, the white material you see shedding from the vehicle is simply ice. Modern rockets carry enormous amounts of liquid oxygen, and many also use extremely cold propellants like liquid hydrogen, methane, or even chilled kerosene. Liquid oxygen sits at minus 183 degrees Celsius. Liquid hydrogen is even colder, at minus 253 degrees. Those temperatures turn the rocket's tanks into massive airborne freezers. As the vehicle waits on the launch pad, moisture from the surrounding air condenses on the chilled metal skin and freezes solid. That's why, before liftoff, you often see thick white frost spreading across the rocket's exterior. When the Saturn V was fully fueled, it would rapidly become buried under sheets of ice, looking less like a spacecraft and more like an industrial freezer that hadn't been defrosted in years. That ice wasn't just cosmetic. Like ice trapped inside a frozen lake, it contained large amounts of air, which meant it actually acted as insulation. But once the engines ignited, everything changed instantly. The rocket experienced violent vibration and deafening acoustic energy, essentially shockwaves ripping through the air. That intense shaking broke the ice loose, sending it crashing down the sides of the booster. There's no official figure, but rough estimates suggest hundreds of pounds, somewhere between 50 and 100 kilograms of solid ice falling away during liftoff. And yet, it almost never mattered. The ice didn't have enough time to accelerate to dangerous speeds, and there was very little for it to hit other than aluminum fins near the base. So it became a normal, expected part of launches, dramatic to watch, but largely harmless. Most of the time. Because sometimes, falling debris isn't harmless at all. And when it isn't, the consequences can be devastating. That's where China's rockets enter the picture. Because in many Chinese launches, that white material isn't ice, it's insulation. On several Chinese launch vehicles, especially the Long March 2, 3, and 4 families, the white debris seen falling away is not frozen condensation. It's thermal insulation. Specifically, insulation foam and protective coverings designed to regulate temperature and shield critical systems. Visually, it appears as uneven white flakes or torn sheets that seem to rain downward shortly after liftoff. But these pieces aren't being violently ejected. Instead, the rocket accelerates away so rapidly that once the insulation detaches, it's simply left behind, slowly tumbling through the air at relatively low speed. These rockets rely on hypergolic propellants, primarily unsymmetrical dimethylhydrazine and nitrogen tetroxide. Both remain liquid at normal temperatures, but nitrogen tetroxide has a very narrow margin between freezing and boiling. That narrow margin matters a lot, because many Chinese launch sites are located far inland, where temperatures can swing dramatically, not just between seasons, but even between day and night. In winter, temperatures can plunge well below freezing. In summer, they can climb past 30 degrees Celsius. Without insulation, the oxidizer could freeze in cold conditions or begin boiling during extreme heat. Even modest temperature shifts can interfere with valves, seals, wiring, and guidance servos. Insulation keeps those systems within a narrow, safe operating window before and during launch. The insulation itself is typically spray-on or molded foam, similar to polyurethane or polyisocyanurate. This type of material is often associated with cryogenic rockets, but it's also widely used on non-cryogenic vehicles to limit heat transfer, prevent condensation, and buffer against harsh environmental extremes. On Chinese rockets, insulation can cover propellant tanks, feed lines, engine skirts, interstage sections, umbilical interfaces, and structural attachment points. During liftoff, staging, aerodynamic heating, and intense vibration, small sections can break free. Insulation also appears on payload fairings. Satellites are extremely sensitive to temperature and humidity. While the rocket sits on the launch pad, the fairing is actively climate controlled. That conditioning system disconnects shortly before liftoff. If a launch is scrubbed at that point, insulation provides passive protection until ground systems can be reconnected, preventing rapid temperature swings that could damage the payload. And not every white object you see falling is foam. Sometimes it's a thermal blanket, a protective cover, or a component designed to be jettisoned. A key visual clue is how it moves. Insulation drifts and tumbles slowly behind the rocket, while structural components or planned separations detach cleanly and decisively. So yes, falling white debris on Chinese rockets is often normal, but that doesn't mean it's always safe, because insulation foam has a history. And sometimes that history turns dangerous. In 2021, Chinese commercial launch company iSpace learned that lesson the hard way. An errant piece of insulation foam led directly to the loss of its Hyperbola 1 rocket. Hyperbola 1 is a 4-stage launch vehicle. On its second flight, it lifted off from the Jiuquan Satellite Launch Center in the Gobi Desert. Moments after liftoff, something went wrong. The rocket began to veer sharply off course, a clear sign of a serious control failure. Hours later, iSpace officially confirmed the mission was lost. What followed was an intense investigation. According to the company, engineers spent 28 days conducting fault isolation, simulations, predictive modeling, test verification, and design corrections. Their conclusion was precise and unsettling. A piece of insulation foam designed to detach harmlessly struck one of the 4 grid fins at the base of the first stage. When that foam finally broke free, it altered the fin's angle. That small change triggered a rapid and uncontrolled shift in the rocket's attitude. Within seconds, the vehicle lost stability and broke apart. For context, Hyperbola 1 stands 20.8 meters tall and weighs roughly 31 metric tons at liftoff. It uses 3 solid propellant stages, topped by a liquid propellant 4th stage. The failure itself was bad enough, but the timing made it eerie. The mission was lost exactly 18 years to the day after one of the most infamous disasters in spaceflight history. In 2003, the Space Shuttle Columbia was destroyed during re-entry, killing all 7 astronauts aboard. The root cause traced back to launch. A piece of insulation foam broke off the shuttle's external fuel tank and struck the orbiter's wing. That impact damaged thermal protection tiles, allowing superheated plasma to penetrate the structure during re-entry. The result was catastrophic. The tragedy carried a cruel irony. The shuttle needed insulation foam to prevent ice from forming on the massive external tank. Without it, falling ice could strike the wings or tail, so foam was sprayed on to stop ice buildup. But under intense vibration, the foam itself sometimes detached instead. And in Columbia's case, that trade-off proved fatal. This is why falling insulation debris is never taken lightly. It may look soft, it may look slow, but when it strikes the wrong component at the wrong moment, it can end an entire mission, or worse. To reduce the danger of falling debris, modern rocket designers have explored a very different approach. One of the most influential comes from SpaceX. It's known as the load-and-go fueling strategy. Instead of fully fueling the rocket hours before liftoff, SpaceX pumps propellant on board at the very last possible moment. This sharply limits the time ice can form on the vehicle. Less time on the pad means less frost, less insulation shedding, and fewer chances for debris to strike critical hardware. But the strategy comes with a trade-off. If a launch is delayed by more than a few minutes, the rocket must be drained completely, and teams must wait for any remaining frost to melt before attempting another launch. SpaceX uses load and go for its satellite missions and cargo Dragon flights, starting the fueling process just 35 minutes before liftoff. The method works especially well because SpaceX uses subcooled propellants. These fuels are denser, which improves performance while reducing boil-off. And load and go isn't limited to cargo. Since 2018, NASA has approved SpaceX to use load and go for crewed Crew Dragon missions as well. That decision sparked controversy. At the time, former astronaut Thomas Stafford, chair of NASA's International Space Station Advisory Committee, openly criticized the plan. He pointed out that it went against decades of NASA human spaceflight practice, where rockets were always fueled before astronauts boarded. The concern was simple. Fueling late introduced new risks, but results matter. Since then, every Crew Dragon mission has launched without incident. Load and go didn't just work. It proved itself under the most demanding conditions in human spaceflight. And that success has reshaped how the industry thinks about fueling, insulation, and launch safety. China is paying attention. Its space program is not locked into legacy designs. Newer rockets and private ventures are already moving in a different direction. One of the most notable examples is Juke-3. Unlike older Long March vehicles, Juke-3 uses a stainless steel structure and different propellant choices, opening the door to new insulation strategies and full reusability. Rather than relying on large external foam panels that shed during ascent, these newer designs use insulation only where absolutely necessary. That mirrors the approach taken by modern Western rockets, including SpaceX systems. On December 3rd, Beijing-based launch company Landspace sent its Juke-3 rocket skyward from a remote desert site in northwestern China. For a debut flight, the stakes were enormous, and for the most part, the mission went exactly as planned. Juke-3 successfully reached orbit on its very first launch, a major technical achievement for any new orbital rocket. The only issue came later, during the recovery attempt. As the first stage engine reignited for landing, an anomaly occurred. The booster failed to achieve a controlled soft touchdown and instead impacted near the edge of the recovery zone. The recovery test was lost, but the launch itself was a success. That distinction matters. Reusability is hard, and first flight landings are rarely perfect. Even SpaceX needed multiple attempts before Falcon 9 boosters began landing reliably. What matters is that every other phase of the mission performed as expected. For Landspace, that places Juke-3 well ahead of many competitors in China's fast-growing commercial space sector. This single test has pushed Landspace to the front of a crowded field of Chinese companies racing to develop reusable rockets. Reusability isn't optional anymore. It's the key to lower costs, higher launch cadence, and global competitiveness. And China knows it. As China develops more reusable launch vehicles, some built entirely from stainless steel, the visual similarities to SpaceX rockets are hard to ignore. So why do so many Chinese designs look familiar? The answer is simpler than it seems. Good engineering converges. When a design works, others naturally adopt the same solutions. No rocket illustrates this better than Falcon 9. Since its first flight in June 2010, Falcon 9 has completed over 500 orbital missions. It has suffered only 3 total failures and 1 partial failure. Hundreds of Falcon 9 first stages have successfully landed on drone ships at sea or back at their launch sites. That reusability has dramatically reduced costs and transformed SpaceX's business model. Falcon 9 also succeeds because it avoids unnecessary complexity. Its reusable first stage uses 9 engines running on the well-understood gas generator cycle. The expendable second stage uses a vacuum-optimized version of the same engine design. It burns a proven propellant combination, RP1 kerosene and liquid oxygen. The true breakthroughs weren't exotic engines. They were autonomous landings and protecting hardware during atmospheric re-entry. Some of that foundation traces back to earlier programs like NASA's DCX. Over time, SpaceX refined durable thermal protection systems capable of surviving multiple flights. Falcon 9 proved you don't need an overly complex design to achieve high reliability and true reusability. And since the laws of physics don't change by country, it makes sense that others would follow the same path. Then there's Starship. Unlike Falcon 9, Starship burns methane instead of kerosene. That choice wasn't cosmetic. It was strategic. Kerosene combustion leaves behind soot, forcing extensive engine inspections and refurbishment between flights. Methane burns far cleaner, producing almost no residue. That makes rapid, frequent reuse far more practical, exactly what Starship is designed for. SpaceX also chose stainless steel for reasons that go beyond appearance. It offers a rare combination of low cost, high temperature tolerance, and manufacturing simplicity. It's easier to weld, more forgiving during testing, and performs well at extreme temperatures, all critical traits for a vehicle meant to fly often. That same logic is now shaping next-generation rockets around the world. So when modern Chinese launch vehicles start to resemble Falcon 9, Starship, or even a hybrid of the two, it shouldn't be surprising. These architectures work. They've been tested, proven, and refined through hundreds of flights. When engineering solutions reach this level of efficiency, designs naturally converge. But resemblance alone won't make China competitive. To seriously challenge Western launch providers, Chinese reusable rockets must be both affordable and consistent. Flying once isn't enough. Flying reliably, again and again, is what lowers costs and wins customers. The encouraging sign is that China's launch market is already moving in that direction. Roughly a dozen private companies are actively developing reusable rockets. Most plan to start with just a few launches per year, then scale to monthly, and eventually weekly flight rates. That's the same trajectory SpaceX followed a decade ago. With SpaceX setting the benchmark, technical success alone won't be enough. Consistency, cadence, and cost will decide who leads the next era of spaceflight. And as China's rockets continue to evolve, from insulation foam to stainless steel, one thing is becoming clear. The global launch race is no longer about copying designs. It's about mastering them.